IT, so it's coming from the projector. It's, I think it's the fan.
You're like on top of your efficiency.
I don't like having things like hanging. So the other piece that happens is kind of all my classes are on a similar time frame. So like all the tests are happening kind of at the same time. So like I can usually grade one class while the other class is taking theirs, and allows me to turn things around pretty quickly.
Yeah.
These are things that you figure out that you can do after 15 years on the job. It's like, this just makes life easier. Oh, my first year I think was 08. And I taught 2 years prior to that elsewhere, so.
Are you in the same room?
The whole time I've been here. Yeah. It's a good one, I guess. All right. Today we'll be starting chapter 4. This first section in chapter 4 is an extremely important section, as it's like a foundational piece to a bunch of future chapters. So this is one where we'll take a fair bit of time. We'll do this carefully. We'll do it slowly.
Now I'm just scared.
But this is one that, like, it's not a this matters for this chapter topic. It's a this matters like a bunch of places going forward topic. So we definitely want to make sure that we do a good job here. Similar to like in Algebra 2, like factoring is a really important skill. Like that comes up over and over and over again. Being able to solve a quadratic is a really important skill that comes up over and over and over again, especially in future chapters. So you really want to make sure you do a good job at that point with that topic, because it becomes a sub-skill a bunch of other places. The same is kind of true here. Okay? So we're going to start in section 4.1 is just talking about, is my stuff going to work? There it goes. Only if you have a few $1,000s laying around to replace it. All right. So section 4.1 is about the inverse trig functions. And I'm going to do the conceptual piece. I'm going to talk about it and generate some graphs and kind of explain what's going on. Well, that helped. All right. So let's say we're just going to start by looking at the sine function. Okay, so this is the graph of sine. This should look familiar. We just got done graphing stuff, right? Let's say that I wanted to find the inverse for this function. Maybe let's step back one step here, right? Let's step back one step. So recall, if I can do sine of something, what kind of things can I plug into the sine function? Angle measure, right? Sine of an angle gives us a number, right? What if I had the number and I wanted to get the angle back. What we do here is we use an inverse function. So the name we give for the inverse function for sine is sine inverse. Sine inverse takes a number and turns it into an angle measure. Everybody's okay with that? So remember, if I have some function y equals f of x, and I want to find its inverse, what do we do? We swap the x and y's. Right? That's really all we're doing. Is I want a function that takes, I want the output when I plug it in to give me the input, right? I should probably change the name of this thing because it's not necessarily F. Come on. Hi, Eden. Well, if you take a listen. Hey, everybody, can you be quiet for a second while he listens? It just turned on. As soon as this turned on, it started, right? If I turn this off, as soon as the power cuts, it's gone. I turn it back on, it'll boot up and...
Does anyone have headphones in their backpack or anything like that? This could be connected. Anybody got headphones connected? We had one class where someone's headphones was like, you know, the sound was did it sound like a hearing aid? Remember, you ever have someone near you that has hearing aids that buzzes?
Oh, I don't know.
It's like almost like a whistle sound. Is that what it was like?
Well, listen again. Here it comes.
I just feel like it's not that great.
But it sounds like it's coming from the projector, not from a headphone. And to me, it sounds like it's coming from the fan piece. I don't know what other moving part would be on there to be able to make a noise like that. Yeah.
But things are working. I'll come back.
Yeah, it's working right now. I just wanted to give you guys a heads
how
up.
loud it was.
Right, yeah. I mean, it's just annoying. It's not like getting in the way of anything.
When I went away after a little bit, though.
It feels like it cycles in and out, I think, again, because, which would make sense if it's a fan. Like, if it's cooling, or if it gets cool enough and the fan kicks off, it feels like it kind of stops for a second. Yeah.
Okay. I'll come back to you.
No problem. All right. Hi, everyone. So let's take a look here then. So here's we're going to talk about sine here in particular, right? So here's the graph of sine. When I swap the x and y coordinates to generate the graph of its inverse, what do you notice?
Now it's going up.
Mm-hmm. Do you notice anything problematic with that blue graph?
It's not a function.
It's not a function. Very good. Why is it not a function?
Vertical line test.
It fails a vertical line test. Great.
Even I knew that.
That's excellent. I'm glad you knew that.
I love that test. That was a good one.
All right.
That's the only test I passed.
So
Currently not.
that's a problem for us, right? Because ideally what we want to be able to do is be able to write a program that we can program like a computer or a calculator where we can input the number and output the angle measure. Now, something that's not a function, it creates a problem doing that. So we're going to have to fix this, okay? So what we're going to do is we're going to take our original graph of sine and we're going to restrict its domain. So I'm going to restrict its domain so that none of the y-coordinates are repeating. So that little piece of green is all of the sine function we're going to take. It covers the entire range of sine, all the y-coordinates that sine hits, that green graph covers, but none of the y-coordinates are going to repeat. Everybody's okay with what I did there?
What did you do to restrict the domain?
I just cut it off. I just cut off the rest of things.
Do we know how to do that?
No, I'm just talking about what we're doing.
Oh,
So like, let's make that a different color. So if I look at this red, I said, okay, I know the range of sine goes from -1 to +1, correct? So I'm going to go, okay, where does this take on the value of -1? Here at -2. So I'm going to cut off everything before that. And where does it hit the y value of 1? You're at +2. So I'm going to cut off everything on my graph after that. And that'll make sure that I have the entire range covered, but I don't get any repeats. Does that make sense there as to what I did? Okay. Now, if I swap the x and y coordinates, what I get is the blue. What do you notice? Well, the blue's a function now, right? That's the piece that I want. Okay? So that's what we're doing. Notice though, the domain for the blue isn't all real numbers. I can't plug in any value or any number into the blue and still get a y coordinate to come out, correct? And furthermore, the y values that come out only cover so much, right? I can't get any angle to come out of this thing. Everybody's okay with that? That's going to be the part that requires some finesse from us. So this is what's programmed into your calculator. You can input values between -1 and +1, but it's only going to output values between -π/2 and +π/2. If we're looking for a different angle than one that lies in that interval, we're going to have to kind of make some adjustments so that we can get the actual angle we're looking for out. Okay? So let's summarize a little bit of what we did here. So we have the function sine of x. The domain for sine of x is all real numbers, and its range was from -1 to +1. What we did is we restricted its domain to -π/2 to +π/2. In doing so, though, the range still remained the same. That was the minimum amount of x's that we could keep and still keep the range the same. Everybody's okay with that? Our inverse then, when we created that, its domain is going to be the same as the range for our restricted sine function. and its range is going to be the same as the domain for our restricted sine function. Is everybody okay with that? So far, so good? We could do a similar process for cosine. And we can do the same thing for tangent. Is my eraser not working on that pen? Okay. So, Mr. Kulik, so what? Right? So what? Well, student, this is the piece that you need to make sure that you remember. Is you need to remember the range for each of these three inverse trig functions. You need to remember what angles the calculator can output. Matthew?
For the tangent,
I-
after all real numbers
Mhm.
x equals, what does that say? N over 5?
Yeah,
And then what's that?
where n is equal to an odd integer. But that all doesn't matter. We just restricted it down to one period. Here's a little question based on previous. Notice the range on tan inverse and sine inverse are different. One is a bracket, one is a parenthesis. What does the bracket versus parenthesis mean?
The bracket means like, wait,
Olivia, is that a hand? Great, so the bracket means that value is included, means you could plug negative pi over 2 in, or negative pi over 2 is a value that can come out of sine inverse. The parenthesis means it's not included, meaning that negative pi over 2 cannot come out of tangent inverse. Okay, why does it come out of sine inverse but not out of tan inverse?
so like for the tan, those range values are the spot where like the function can't go over.
Why? What is there in the graph of tangent? Yes. So Nate says that those values, negative pi over 2 and positive pi over 2, are the locations of asymptotes in the graph of tangent. The asymptote is where the function is undefined. So I can't plug undefined into my inverse to get a value to come back out. That's why. In sine and cosine, there are no asymptotes. So that's why the endpoints of our restricted domain can be included as values to come out of the inverse. In tangent, though, negative pi over 2 and positive pi over 2, the endpoints of our restricted domain are the locations of asymptotes. That's why they cannot be included in the restricted domain and they cannot come back out of the inverse function. Okay. So let's do some stuff on our calculator. Oh, as an aside, yeah, somebody left their calculator on the charger, and one of you crooks left with my other red calculator after our test. Okay, I believe you, but some other thief in here has my other red calculator. Well, all 4 of them got borrowed. 3 of them came back.
Guys, come on. Hey, I'll pick up the right here. It has a duck on it. Well, mine has a sticker.
Right there.
You got robbed. What happened?
Okay.
We're gonna need to run an investigation.
Well, here you go, detectives.
Seriously?
It says property of NDP on it in magic marker. You find it and return it to me. I'll make it worth your while.
Do they have the cover of it too?
Yeah, they got the whole thing. Okay.
We'll hunt them down. Bree. What?
Bree,
No, I
Bree got
have
the-
a funcking calculator. We got
Can I borrow it?
Sure.
I'm just too good. I don't need them.
I give calculators back. I'm like someone in here.
Yeah.
I think
David?
Saul has.
And I guess I'm 90% sure it was after this test. I have to admit it. I noticed it later. Then I'm like, well, I'm short a calculator. Like, well, I loaned 4 out. I don't remember getting 4 back.
Did all 4 get used in here?
Yeah. Because remember, Bree had to use the giant, that stupid 4 function calculator because they all were borrowed.
Hey, but we
have mine.
I still don't good.
Yeah, you did all right.
I didn't know I had mine.
All right. Oh.
I don't need borrow.
I don't remember what it specifically was, but
Yeah.
there weren't any colossal failures in here, so, you know.
Really?
Yeah.
No, I just borrowed all the time.
All right.
Dude, I think it was
He's so suspicious.
Do all your items are a bunch of back.
But did you?
So, when we're using the inverse commands on our calculator, there's a couple of things that we have to be concerned with. Okay, so when we're using our calculator, or using one of these inverse functions on our calculator, Couple of things we have to be careful about. Number one, the mode of our calculator matters when we're using these. So go ahead and press the mode button. Depending on the context or directions of the question might ask you for angles in radians or angles in degrees. If you want a radian answer, what mode should your calculator be in? Radians. If you want a degree answer, what mode should your calculator be in? Degrees. Does it matter if I do like 5 times 7, what mode my calculator's in? No. Only if I'm using sine, cosine, tangent, or sine inverse, cosine inverse, cotangent inverse, or tangent inverse, right? Those are the only functions that the mode of your calculator matters, okay? If you're doing square roots or whatever, the mode doesn't matter. But here it does. Let's put our calculator in radian mode, if it's not already there. And then I'm going to do cosine inverse. To get the inverse cosine, you have to press the second button, that's the blue one, and then press the cosine button. And then I'm just going to type in negative 0.57, close the parenthesis, and press enter. So that's the angle measure in radians for cosine inverse of 0.57.
I could take a chance on doing that.
So I'm going to write, I normally wouldn't write radians here, but I really just want to reinforce that what you're getting back is an angle measure, because that becomes a conceptual misunderstanding for students. So we're going to really kind of emphasize that quite nicely. All right, let's do the next one. Tangent inverse of 2.55. So I get 1.2. Why don't you guys try sine inverse of negative 1.57? Error, says Emma. Oh no. Did Emma make a mistake? What do we think? Did Emma make a mistake? It says the error kind is a domain error. So let's go back and look at our sine inverse information. What's the domain for sine inverse?
Negative 1, 1.
Negative 1 to positive 1. What are we putting in?
Negative 1.
So this should have no solution. That should be the case. When we plug in for sine and cosine, we do have to be careful because the domain of sine and cosine is only negative 1 to positive 1. Notice that that's not the case for tangent. You can plug anything you want into a tangent inverse. But sine and cosine inverse, you are restricted from negative 1 to positive 1. Everybody's okay with that? Okay.
Just do it on your computer and print it out. You got cots. Yeah. It's really
All right. Next set of examples. Here it says to find the exact value of each angle, and I give you a bunch of these to do. What about this definition or direction is different than the previous one? In the directions?
Oh, no, but exact.
Yeah. When we're in trig and you hear the phrase exact value, what tool are we almost certainly going to need? No, not the calculator. You put the calculator away if it's an exact value.
The unit circle.
The unit circle. Very good.
That's how the unit circle like died and you put it in its grave.
No, it never goes away. It's like a zombie. It just keeps coming back to life over and over again. It's like Night of the Living Dead, except it's a unit circle. The Night of the Living unit circle. All right. So, first thing I'm going to need to establish, I need to remember what the domain is. I'm sorry, the range is for sine inverse.
That would be negative pi over 2.
Very good. Everybody's okay with that? What quadrants of the xy axis are covered by the angles from negative pi over 2 to positive pi over 2? So remember, when I draw an angle, I start at the positive x-axis. If it's a negative angle, which way do I go? Clockwise. So to here would be negative pi over 2. What quadrant is this that I've covered here? It's quadrant 4. If I go in the positive angles, or if I'm doing a positive angle, which way do I rotate? Counterclockwise. So again, starting at the positive, I go here to positive pi over 2. What quadrant did I cover there? 1. So we're looking in quadrants 1 and 4 is where we're looking. Everybody okay with that? So far, so good? Shh. This statement, theta equals sine inverse of root 2 over 2. This is equivalent to saying sine of theta should equal square root of 2 over 2. Everybody's okay with that?
Wait, what?
That's just the definition. If those two things are inverses, the output of the inverse, if I plug it into the other function, should give me the input to the inverse, right? That's all we're saying. On the unit circle, how do I find sine? It's the y coordinate. So what I'm going to do is I'm going to look at quadrants 1 and 4 on the unit circle. for the place where the y coordinate is the square root of 2 over 2. That's the only place that that occurs. Everybody agree? If I look at every other y coordinate in quadrants 1 and 2, that's the only place. So my answer should be pi over 4. Done.
So, hypothetically speaking, we could have just gone from the start right away to the answer because.
Well, how did you know it wasn't this one? Yeah.
Wait, how did you know about the square root of 2 over 2?
It's in the problem. It's given to me in the problem.
Oh, yeah. So we need to have the range.
Yeah, you're going to use the range from the function to figure out the quadrants you need to look in. Then you go to the quadrant and find the desired result. Matt.
How did you use the range again?
So we use the range to figure out the quadrants. Let's do it again. Right? All right, let me erase this stuff out of here. What's the range for cosine inverse?
0.
Okay. What quadrants are covered by the angles from 0 to pi? The top two. Remember, when we start graphing positive angles, we start on the positive x-axis, and we rotate counterclockwise. So that's pi over 2. Keep going. All the way here is pi. So we covered all of quadrant 1 and all of quadrant 2. So in quadrants 1 and 2 on the unit circle, I'm going to look where the x-coordinate is negative root 3 over 2. Everybody's okay with that? So my answer is 5 pi over 6. Pat? Sure. Those are just the names we give them.
Well, yeah, I know.
And we name them counterclockwise.
I just don't understand how to figure out which quadrant.
So I'm drawing a standard position angle, right? A standard position angle starts on the positive x-axis and it rotates. If it's a positive angle, like 0 to pi, those are all positive angles, it's going to rotate counterclockwise. So I'm just going to start going this way. So up to here is pi over 2. So I'm going to keep going. To here is pi. So I've covered all the angles that live in quadrant 1 and all the angles that live in quadrant 2. And then I stop because that's where my range ends. Does that make sense?
Yeah.
So I'm not doing any calculation. I'm just kind of looking with my eyes. Let's do the next one, right? What's the range for tangent? Okay. And which quadrants does this lie in? We already kind of did this. 1 and 4. Should be the same as sine, right? Now I'm going to go to my unit circle and look for the place where Tangent, remember, is y over x. But this is a little bit more complicated, right? Because y over x was a fraction, it's very likely that this is something that was reduced. Everybody's okay with that? So what I'm really going to look for is a place where the y-coordinate has a square root of 3 in it, and the x has a 3 in it. Do you see any places where there's a regular 3 on my unit circle? No. Okay, what should I do then? Because that's just how Mr. Kulik told me to look for this. Not a 6. What I'm going to do is I'm going to reduce this fraction. How can I reduce this fraction? I'm going to think about that denominator of 3 as the square root of 3 squared. Is everybody okay with that? So I can reduce this to be 1 over the square root of 3. So now I'm going to look for a place where the x-coordinate is, or the y-coordinate has a 1 in it, and the x-coordinate has a square root of 3 in it. That's something I see, right? For example, there where the y, I put them in here, where the y has a 1 in it, and the x has a square root of 3 in it. Now that's not the right spot, because where should I be looking? Quadrants 1 and 4. What else do I notice here? One of them has to be negative, so it has to be looking in quadrant 4. So I'm looking for this spot here at 11 pi over 6. The tangent ones are a little bit tougher because it's not an immediate, like, just look for the number in the right spot. You have to kind of look for part of the number in each of the 2 spots. Is that okay with everybody?
Sure.
Sure. Okay. What do you notice that's weird about number or letter D? Secant. Yeah, it's the inverse of a reciprocal. Yeah. So I know that theta equals secant inverse of the square root of 2 is the same as secant theta equals square root of 2. That's just our inverse definition. And Nathan pointed out that secant is one of our reciprocal functions. It's the reciprocal of which function? Cosine. So I know secant theta is the same thing as 1 over cosine theta. Everybody's okay with that? And that's an equation. So I can do things to both sides of this equation. Like, for example, do the reciprocal of both sides. Everybody's okay with that? Notice that I could rationalize this denominator. And then I'll end up with something that looks a little bit more unit circle-y. And if I rewrite this now as an inverse, I have a problem that looks just like part B. So I know that the range for cosine is 0 to pi, which is quadrants 1 and 2. So I'm going to go to my unit circle and look for the place where x is equal to positive root 2 over 2. That happens there at pi over 4. And I'm done. I want to point out to you something here. If I look at this and I look at this, what did you notice? I swapped out secant inverse for the reciprocal inverse and then took the reciprocal of the inside, right? Do I need to do all that algebra to justify doing that when you do it? No, you could just remember that's how you do the problem, and that's fine. You don't have to show all the algebra that I did to justify it. But I think it helps seeing that so you can understand why that works. In case you're like, oh, what was the rule again? You could just kind of like fiddle through it yourself. Can I point something out to you? Each of these problems should be checkable. May I show you how to check these? So I'm going to do that with my calculator now. So if looking at checking part A, if I do sine of pi over 4, I should get back root 2 over 2. So there's my decimal, and I'll observe that this decimal is the same thing as root 2 over 2. So that looks like it checks out, but there's one more thing I need to check. What else do I still need to check? I need to check to make sure that this answer lies on the interval for my range. So I need to make sure that pi over 4 is bigger than negative pi over 2. Well, clearly it is, because it's a positive number. All right. And smaller than pi over 2. Well, that's clearly true, because a quarter is definitely smaller than a half. So I'm happy with that one. That looks good to me. Let's check the next one. You guys happy with doing this? This makes sense, how I'm checking this? Okay. So here we're going to plug 5 pi over 6 into cosine and should get back negative root 3 over 2. And just check that real quick. Notice when I typed in negative root 3 over 2, the divide by 2 is not under the radical. Very important that you type it in that way. They match. Great. And then I need to check to make sure 5 pi over 6 is between 0 and pi. Well, it's definitely bigger than 0. And 5/6 is less than 1. So it's definitely smaller than pi. So I'm good. Everybody feel good with what we're doing here? Okay. All right. One more twist now. Okay, one more twist on what we're doing, and then we're going to stop where we're at for today. So my new direction says find the exact value of the angle on the given interval. Notice here we have this additional direction on the given interval. Bless you. I'm sorry. That's not going to work. One moment. I'm going to change that interval here. Come on. There we go. My apologies. All right. Everybody ready? So, here, instead of using the range for cosine inverse to get to figure out where my answer is, I need to use the given interval. So I need to figure out what quadrants are covered by 3 pi to 4 pi. The way I'm going to do that is I'm going to just draw myself a picture. So when I start drawing a standard position angle, I start on the positive x-axis. And if my angles are positive, like 3 pi and 4 pi, which way do I rotate? Counterclockwise. So here's a half, 1 pi, 1.5, 2 pi's, 2.5, 3 pi. So the start of my interval I'm looking on is here. 3.5 to 4 pi. What two quadrants did I cover there between 3 pi and 4 pi? Quadrants 3 and quadrants 4. So I'm going to go to the unit circle, and I'm going to look for where the x-coordinate is -1/2 in quadrants 3 and 4. So if I go back to my unit circle, looking for where x is -1/2 in quadrants 3 and 4, the only place that occurs is at 4 pi over 3. Everybody cool with that? What's the catch, though? That this is smaller than 3 pi. Too small, right? It doesn't lie between 2 pi and 3 pi. What should I do? I need an equivalent angle, an angle where the cosine is still the same value, but is bigger. Does this remind you of anything we did in a previous chapter? The term starts with the letter C. C-O, C-O-T, C-O-T-E, coterminal. What we want is an angle coterminal to 4 pi over 3. Do you remember how we find angles that are coterminal?
We add 360.
We add or subtract. In this case, I wouldn't use 360 though, because we're in radians. I would use 2 pi. Should I be adding or subtracting? Adding, because my number currently is too small. Okay? So if I add 2 pi to this, I need to make a common denominator. What would my common denominator be? 3. So I'm going to get 4 pi over 3 plus 6 pi over 3, which would give me 10 pi over 3. 10 pi, or 10 thirds, is 3 1/3, right? That's bigger than 3 pi and smaller than 4 pi. So that'll do it for me. Yes, Kate. Coterminal. So I'm just going to find something that's coterminal then to the answer from the unit circle. If it doesn't lie in the interval that I need, then I'm just going to find something coterminal to it that does lie in the interval. Because it's going to give me this, it's going to have the same x value. It'll just be a bigger number, a smaller number. Let's do another, yeah? Okay. Yes, sir.
Are you Canadian?
No, sir. Why?
Are you Irish?
Nope.
Are you Scottish?
No. Polish would be the primary ancestry.
Heck yeah. What else?
I don't really know what's on my mom's side. It's kind of a big mess, I think.
I'm very Polish.
You are?
Yeah. Only true Polacks. I'm New York. I was thinking more of
All right. Here's another example. Here's another example. How do we start? Yeah, we start with the interval and figure out what quadrants we need to be looking in. So when we draw our standard position angle, it always starts from the positive x-axis. And since our angles are negative in this case, we got to go clockwise. So this is negative pi over 2 here. And then negative pi. And then negative 3 pi over 2. What quadrants did we cover? Quadrants 2 and quadrants 3. So I'm going to go to my unit circle and look for where y over x is equal to the square root of 3. Or really, I'm going to think about it as the square root of 3 over 1. So I'm going to look for something where the y-coordinate has a square root 3 in it, and the x-coordinate has a 1 in it. Note that here, it's a little bit tricky. Notice that square root of 3 is positive, but in quadrant 2, the x's are negative and the y's are positive, so both of them couldn't be positive there. In quadrant 3, the x's are negative and the y's are negative, so there wouldn't be positive in both of those. Uh-oh, did I make a mistake? No. Well, in quadrant 3, where both of them are negative, what's negative divided by negative? Positive. So I really should be looking in quadrant 3, right? Okay. So I'll go to quadrant 3. I'm looking for a place where the y-coordinate has a square root of 3 in it, and the x-coordinate has a 1 in it. So I have 4 pi over 3. Now, does that lie in my interval? No, it's clearly bigger than both of them because it's positive. Oh no, what should I do? Yeah, we'll find something coterminal by subtracting 2 pi. To do that, I need to make a common denominator. So that's going to really be 4 pi over 3 minus 6 pi over 3, which is going to give me negative 2 pi over 3. Now, negative 2/3 is smaller than negative 1/2, right? Remember, negative numbers, like kind of the bigger the negative looks, the more negative it is, so actually the smaller it is. And negative 1.5 is definitely smaller than negative 2/3, 0.6. So I think we're good. What do you guys think? This is okay? All right.
My favorite subject.
So for your assignment, I'd like you to work on 1 through 6, and then worksheet 1. And that would be due November 6th. That sounds right. Just got so used to writing 10s. Okay, what's due this weekend? I think just the review is the only thing on the docket, right? Everything else I think we've checked.
Yep.
Okay. Which I'm guessing most of us have already done because we took the test this week. So it should be a light homework weekend for you guys because there's not really anything due that you probably haven't done already. And that's nice. And we're going to stop here.